Years, Dr. Greg Rao has been actively engaged in biochemical research, especially using carbon isotope 13 and other naturally occurring isotopes to address questions about carbon and nutrient cycling. More recently, he has been investigating ways to exploit the natural chemical reactivity of carbon dioxide as a means of cost-effectively capturing and storing anthropogenic CO2. One of these methods has been recently patented, and several others are pending. Dr. Rao is a longtime member of the American Geophysical Union and of the American Society of Limnology and Oceanography, and is a fellow of the American Association for the Advancement of Science. A senior researcher with the Institute of Marine Sciences at the University of California at Santa Cruz since 1986, he is also affiliated with the Energy and Environment Directorate at the Lawrence Livermore National Laboratory. His PhD was awarded from the University of Washington, and this was followed by postdoctoral experience at UCLA and at the NASA Ames Research Center. Dr. Rao is a fifth-generation native of Washington State and lives with his wife, Farina, in Castro Valley, California. Won't you please welcome Dr. Rao to this afternoon's session.
Thank you. It's nice to be here. Thank you for inviting me to come today. I look forward to sharing with you my perspectives on CO2 mitigation. And I also look forward to learning more about the Air Resources Board's thinking and strategies for reducing the state's CO2 emissions. What I'm going to do today is, first of all, give you a little background on why I think post-combustion CO2 capture and sequestration is needed. We're going to briefly go through some of the options for doing that, and I'll give you a little overview of what's going on at Lawrence Livermore National Lab. And then I'll get into some of the specific approaches, chemistry-based approaches that I've been working on for the last few years that could have relevance here in California for mitigating CO2. And in case people have to leave early or I go too long and don't get to the conclusions, I might as well give you the punchline right now, or the series of punchlines here. I guess the first message is that I don't think CO2 can be ignored in addressing California's strategy for reducing CO2 emissions. And the few reports that I've read in preparing for this talk, sequestration did not figure very prominently at all. And I think that this needs to be more seriously considered. Certainly in the longer term, I think we're going to need CO2 sequestration, especially if we continue to burn fossil fuels, and in some of the future scenarios for using fossil fuels for generating hydrogen, for example, or syn fuels. We are not going to forego the use of fossil fuels. We still have maybe a century or more left of this fuel. And until there's some cheaper alternatives to compete with that energy source and something that's really practical, I think we need to think seriously about the reality that we will continue to use fossil fuels. The question is, can we do so in a way that's environmentally safe? And one of the ways to do that would be if we could find cost-effective ways of capturing the CO2 that's emitted in fossil fuel production. And one of the things I'll be talking, whoops, sorry, I advanced just prematurely. And one of the things I'm going to talk about today is possible ways of capturing and storing CO2 through chemical methods that might be more cost-effective than some of the approaches you may have heard about. And the other point I'll be making today is that certainly we need more funding and we need partnering in R&D efforts to really test out to see if these are really practical, feasible for the state and for the rest of the world for that matter. So why mitigation, and why do we need to worry about CO2? Well, I'm not going to go through that story today. Certainly you're well aware of at least one of the reasons why we should be concerned about our CO2 footprint. But you may not be so aware of another reason, and that is the effect on the ocean, in particular ocean acidification. Well, certainly we're aware of the, whoops, I keep pressing the wrong button here, sorry. Whoops, there we go. We certainly are aware of the climate impacts, potential climate impacts of CO2. But as we add CO2 to the atmosphere, we also have to keep in mind that we are also adding it to the ocean, because as we generate this positive CO2 gradient between the air and the ocean, CO2 will diffuse into the ocean. And unfortunately, it doesn't stay as molecular CO2 once it's been hydrated. It forms carbonic acid, and it can further dissociate to form bicarbonate and hydrogen ion. It also will consume carbonate ion as well. So the addition of CO2 to the ocean is changing the ocean chemistry, and most certainly it is going to increase the acidity of the ocean, that is the amount of hydrogen ion, the hydrogen ion concentration in it. So we need to not only mitigate CO2 because of the climate effects, but because this is potentially going to impact the biogeochemistry of the ocean, which we directly or indirectly depend on as our life support. And as an example, one of my colleagues at Lawrence Livermore modeled what the potential impact would be here if we were to, over the next several centuries, consume all known fossil fuels. So we have an emission scenario where we go up and then obviously we peak out and go back down, increasing the atmospheric CO2 to maybe something like 2,000 parts per million. If we were to do that, we can see that the ocean, this is a function of ocean depth versus time here, and this CO2 will penetrate from the surface into the ocean and will cause a significant depression in ocean pH. Now, pH units are logarithmic units, and what this means is a -7 depression in ocean pH means a hydrogen ion concentration that's 5 times what it is today. So that is a huge impact. And what will those impacts be? Well, we don't know what the whole story might be, but there have been some preliminary studies here looking at the effects of adding CO2 to, in this case, a marine planktonic calcifying plankton. As you can see here, this is the ratio of basically carbonate formation to organic matter formation. As you can see, there's quite a dramatic decrease really in the calcium carbonate that this thing is forming as a function of CO2 concentration here. So extrapolating this to the whole ocean, there's reason to be very concerned about this potential, and this provides obviously another reason why we need to mitigate CO2. So the state has responded, again, primarily because of the climate effects, but I would also say that for reasons of ocean acidification, we also need to find solutions to increasing CO2. The state has responded with a number of various different legislation, most notably AB 32. And the task here, the goal that AB 32 lays out is a reduction by 2020 of our CO2 emissions to 1990 levels. There is an interim emissions target here in 2010 that should equal that which occurred in 2000. But what that means is essentially a 30% reduction in business over business as usual CO2 emissions, which is a very, very tall order. And so how are we going to achieve this goal? Well, obviously, this is still being discussed. There's no final plan here. One of the reports that I came across in preparing for this talk was the Center for Clean Air Policy report. And here they claim that almost all of the CO2 emission reductions can be achieved by applying known technologies and methods that on average will have a cost of something a little under $6 a ton. A lot of these methods and technologies, they argue, will be cost negative. That is, they'll actually, through energy savings, et cetera, will actually save us money in the long term. And so, but the average cost they calculate is something like $6 a ton CO2 to do most of the mitigation. Interestingly, they do not require any sort of They do not require any sort of mitigation on the electricity or oil refining sectors. There's also no mention that I could see of need for CO2 sequestration. And they state that even though these strategies will not entirely fulfill the emissions reduction requirement, that if we have methods that cost less than, say, $123 a ton, we'll be able to meet our full target by 2020. Another report that I ran across was the Climate Action Team report that came out March of last year. This differs from the earlier report a little bit. First of all, they include non-CO2 greenhouse gases. They do cover a fuller a number of the sectors emitting CO2, including the power generation sector. And they again anticipate a low net cost in implementing these various strategies, and with in effect a net positive effect on the economy. But again, there's no mention here of CO2 sequestration or the need for that. Now these analyses seem to contrast with reports that I had read earlier evaluating sort of the national and global need to reduce CO2 emissions. This is a report by Pacala and Sokolow. It appeared in Science in 2004. And here they had a business as usual scenario for CO2 emissions, and this is the emission line that they would be required to stabilize the atmosphere at 500 parts per million. And so they basically, what they did was, I can't seem to get this going, here we go. They basically straightened this line. They sort of idealized these two curves, and they had a business as usual curve, and then the curve required of emissions required to meet this stabilization at 500 parts per million. And this gap was the amount of carbon essentially that would need to be avoided or sequestered or somehow not emitted in order for the atmospheric CO2 to be stabilized at this 500 ppm. Now this obviously is a little longer look at the scenario and the emissions scenarios out to 50 years or 50 years from present versus the 2020 scenario. But there's some other interesting differences here. First of all, really all they're asking for here is a flat line for emissions. This does not seem to be working well. I'm going to try something else here if I can. I guess the people on the web won't be able to see this, but this I can't seem to use the arrow very effectively with the other instrument. Business as usual, you'll notice that the emissions that they're calling for to stabilize atmospheric CO2 is basically a flat line. In other words, they're not calling for a reduction in CO2 over, say, 2000 or 2005 levels, as opposed to the AB 32, which actually is a more dramatic reduction. And also the 2050 target of 80% below 1990 levels is obviously not a component in this particular scenario. So in some ways, this is an easier task than what AB 32 and some of the other legislation is calling for. Yet in this report, they call for really draconian application of existing technologies that would include aggressive CO2 capture and storage, especially in the context of hydrogen and coal to synfuel production. So this seems to contrast a bit with some of the reports I've seen for California's strategy. Another analysis was done again by my colleague Ken Caldera and others at Lawrence Livermore Lab. Now this basically asks the question, what do we need, what level of atmospheric CO2 do we need, or would be our target, depending on how sensitive the climate is to CO2 and what sort of how much global warming we're able to tolerate. And obviously these are subjective questions, but let's suppose based on research that that I know about, that say mean climate sensitivity is something on the order of 2.5 degrees per doubling of CO2, And let's suppose that we are trying to avoid warming above 2 degrees C. Well, in that case, we need to stabilize here at about 500 ppm CO2. If this is our target, and knowing what our future energy demands are going to be out 50 years, we can plot, or he could plot, how much carbon-free energy addition do we need to make per day in order to meet this target and still satisfy our energy demand. And basically what this calls for is about a gigawatt per day of new carbon-free energy globally in order, over the next 50 years to reach this target. So how would we do that? What sort of carbon-free energy might we use? Well, there's the usual suspects: biomass, wind, solar. All of these could do it, but if you look at the land requirements involved to do this, this is per day the amount of land and application of these energies would be required to fulfill a 1 gigawatt per day increase in fossil fuel emissions. So it's quite a ambitious task to think, if we think that we can do this all with these renewable energies. Of course, nuclear is another possibility, but again, we've got to build one of these plants a day basically to satisfy that. This seems to be on some sort of automatic forward here. So anyway, the bottom line here is that while these are going to be able to contribute to lowering CO2 emissions and to contribute to a carbon-free energy sources, it's unlikely that they're going to be able to meet the whole goal. And this seems to imply that we're going to continue to use fossil fuels, but we're going to need to do so in a more carbon-conscious way, and that's going to require CO2 sequestration. So what's the role here of CO2? What's the potential role here in sequestration here in California? What it would do would reduce the need. If we could find cost-effective ways of doing this, it would reduce the pressure that is going to be on efficiency and renewables to fulfill these CO2 reduction goals. And as I said earlier, it's likely that fossil fuel energy sources are going to continue to be needed, and if that's the case, then we need to find ways that reduce their CO2 footprint, and one way to do that is with sequestration. And the other thing is that there could be methods of sequestering CO2 that actually can compete with the cost of using renewables and or efficiency. And if that's the case, then they could readily be thrown into the mix of things that we can do to reduce the overall state CO2 footprint. So what are our options for capturing and storing CO2? Well, if we're not going to put CO2 in the air, there's really two options. Either we can put it on or under the land, or in the ocean, or under the ocean. And there's been a variety of ideas and strategies for doing this. The most well-known one and the most, I'd say, heavily researched one is the abiotic or chemical molecular capture of CO2 with purification and storing it underground. This is a very large program with DOE and elsewhere in the world, and it's been very aggressively, being very aggressively researched. One of the big hurdles here is how to reduce the cost and energy penalty of CO2 capture and molecular CO2 purification. In any case, there's a large research effort going on in this area. Another idea is to enhance the biological uptake and storage of CO2. As we know, plants take up CO2. If we can manage them in a way where that organic matter is not subsequently decomposed and released as CO2, if we can figure out ways of storing the carbon that's captured in this way in a good way, then perhaps there's some potential here for us to reduce CO2 imprint by absorbing CO2 out of the air. There's some carbonation and mineralization approaches. That have been looked at. I'll mention some of these in more detail later. On the ocean side, again, if we could generate and purify pure CO2 or purified CO2 from dilute waste streams, we could inject that either into the ocean or under the ocean. The downside here, as I pointed out, is that there is a chemical consequence of adding molecular CO2 to the ocean, so you in effect will acidify the ocean with this approach, so there's some environmental concerns about doing that, in addition to the cost, again, of trying to capture and purify CO2. We can enhance the photosynthetic uptake of CO2 by ocean plants, phytoplankton, again, as we did here on land. That's been looked at, in particular, adding iron or other trace nutrients in order to stimulate photosynthesis. This is another idea that has been pursued. It could be cost effective, but there are concerns, biological, environmental impacts of doing this. And there also are alternatives, and some of those I'll be talking about shortly. Before I do that, I want to just give you a little overview of Lawrence Livermore National Lab's activities in this area. I work in the Energy and Environment Directorate, and there's 4 major programs in this directorate. And the CO2 mitigation part of the activity here is in the Earth Systems Science and Engineering group. And within that group, there is the Carbon Management and Fossil Energy program. There's also a Water and Environment program, Climate Change Prediction program, which maybe some of you are aware of. There is a fairly large atmospheric chemistry group there as well. And there's also an Energy and Technology and Analysis program. And the various skills and tools that are used there, computer programming, computer modeling is a big part of what Livermore does. They have some very large computer capacity there, so that's certainly a real plus, and certainly one of the focuses even in the carbon management side of things. There's also experimentation of a fairly large geochemistry lab there. There are field programs and verification that do go on, and it is funded by DOE and also with some industrial funding as well. In the carbon management program, really 2 components. One is capture and the other is storage. And on the capture side, there is work going on in membranes, finding membranes that would help us to separate, purify CO2 from more dilute or contaminated streams. This accelerated weathering of limestone is my own area of focus, and I'll talk in some detail about that shortly. There is work going on in desalinization and the possibility of using some of those the same technologies for concentrating and purifying CO2. There's work going on a direct carbon fuel cell also that would much more efficiently burn coal and actually biomass to convert to electricity directly and then generate also a very pure CO2 stream that could easily be mitigated. There's also a large storage R&D going on, a CO2 storage component, and that involves some simulation, large computer modeling. There's a CO2, monitoring and verification of CO2 once it's stored in the ground, and there's some risk characterization and assessment. There is some energy systems modeling and some fossil energy work also going on there. And the various partners that are involved in this, we are involved in WestCarb, which is the West Coast component of DOE's effort to primarily look at capture and geologic storage, although there are other research going on as well, related research going on. There are some companies that we have partnered with in this kind of an effort. The various, again, there are regional partnerships that DOE has set up, one of which is WestCarb, but there are others throughout the country, some of which we're involved in. And various other partnerships, both national and international, that we have partnered with, again, primarily in the context of molecular CO2 capture and geologic storage. Whoops, let's see here. There we go. Because my background has for many years been in global carbon cycling and earth sciences in general, when I first started hearing about the need for CO2 mitigation, my immediate thought was, well, how does nature do this, and could we scale up or modify those processes to provide a system that would help us in lowering our CO2 emissions? And of course, nature does capture and sequester CO2 on its own, and it will do so given enough time. And the three major mechanisms, again, involve ocean uptake, where the CO2 will be naturally absorbed by the ocean. The other way is through photosynthesis, where plants using solar energy can capture and convert CO2 into organic compounds that can be, some of which can be stored a long time. And the other and third way that nature does this is through weathering reactions, and these are abiotic reactions in which, in this case, silicate minerals react with CO2 to form carbonates, or in a process that I'll talk about in some detail shortly, carbonate weathering or limestone weathering, where CO2, water, and calcium carbonate will combine to form calcium and bicarbonate ions in solution. And just as an example of how nature will capture and sequester our anthropogenic CO2, this is a computer model looking at what would happen if we instantaneously doubled the atmospheric CO2 from its pre-industrial levels of, say, 280 ppm to something like 560 ppm. How long would it take nature under these various processes to lower the atmospheric CO2? And as you can see, nature will do this, but it takes something on the order of 1 million years to complete this task. Is there some way we could speed up these processes so that we could mitigate at least some of our CO2 and help speed up this process? Again, what we're doing now is mining fossil fuels, bringing this to the surface, burning this, converting it to CO2. This CO2 diffuses around the globe in the atmosphere. Some of it is reacted out photosynthetically. Some of it is reacted out through weathering. Some of it gets into the ocean, where there can be also subsequent weathering in the ocean of carbonate minerals. Again, this will work. This will be an effective way of reducing atmospheric CO2, but we don't have 1 million years to wait around for this to happen. And our idea is, rather than just simply releasing the CO2 in the air and hoping that these processes will happen, where it makes sense or where it's practical to do so, why not put carbonate mineral and water at the source of our CO2 emissions to do this process right at the tailpipe or right at the point of emissions, converting the CO2 to calcium bicarbonate that we could then put into the ocean or into underground aquifers. So how would we do that? Well, we don't yet know what the ideal reactor would be, but basically what you need is a gas, water, solid reactor. Here's one idea, and you could have the gas stream either entering this headspace or bubbling it through this pile of limestone or carbonate that you have, or underneath it. You'd have a way of wetting this solution, wetting the gases, making carbonic acid, reacting it with the limestone, generating calcium bicarbonate that you would then remove and replace with, recharge with water on some basis, continuously or periodically. Take this waste stream, this carbon-charged waste stream, which would be principally calcium bicarbonate, and again, storing it underground or putting it into the ocean. The idea of wet limestone scrubbing of flue gas is not a new idea. It's obviously done every day, all the time in many coal plants. In this case, mitigating SO2. Again, you're forming an acid, combining it with limestone, and ultimately generating a solid calcium sulfate. By analogy, we're adding CO2 to water, generating carbonic acid, reacting that with limestone, but ultimately generating a solute containing calcium and bicarbonate in solution. So this is not a new concept. Wet limestone scrubbing is already practiced in some energy production schemes, particularly coal. Why not see if we could scale this up to make some impact on CO2? Would this be effective in storing CO2 relative to other methods? Well, here's a comparison where we simply inject some quantity of CO2, molecular CO2, into the ocean versus adding the CO2 first by converting it to bicarbonate in this all process, or accelerated weathering of limestone process. And as you can see, after 1,000 years, it's much more effective to add the carbon in the form of bicarbonate than it is to add it as molecular CO2. So this is another argument. One way that we could use the ocean to effectively store CO2 much more effectively and with much less environmental impact, we think, than adding it as molecular CO2. What would be the consequences to ocean pH? Well, if we add it simply as molecular CO2, we can see what the consequences are, and they're quite dire. There is some impact with the accelerated weathering of limestone because there is some residual CO2 that still remains in solution when we add it to the ocean, but the effect is much less dramatic than it is by using molecular CO2. So from this point of view, it's a much safer, we think it's a much safer way to use the ocean to mitigate CO2. What would it cost? Well, if we have a coastal location where we have ready access to the ocean, we think that we can do this process for $30 or less than $30 or less. And this compares favorably with doing CO2 mitigation by a more conventional amine scrubbing of the flue gas, converting this, concentrating and pressurizing the CO2 and storing it underground, which typically would cost, or is estimated to cost, something like $40 to $60 a ton. So we think we can be competitive in this situation where we have ready access to the ocean. However, we can do a lot better than that under certain circumstances, and in particular, if the limestone is nearby, and especially if it's free. It turns out that about 20% of limestone production in this country is unused. It's simply waste fines that are just sitting around, and they're actually posing a big storage problem for many of these production sites. So if one of these mines was nearby, they had a lot of waste CO2, we could forego a lot of the cost of the limestone and its transportation. On the water side, if we could use the cooling water that the power plant's already using, and in many of these coastal sites they're already pumping massive quantities of seawater for cooling, if we could simply use that on the downside, we could save ourselves some costs in the pumping costs. So in theory, we might be able to do this for $3 a ton CO2, which would be quite competitive if this is true with a lot of other CO2 mitigation options. So it's potentially could be very cost effective, at least in certain locations. So just to overview some of the advantages here, we've got a lot of reactants globally. Carbonates in water are very abundant, but they're not always abundant exactly where you need them. So obviously we need to do that in sites that really make sense and where the reactants are close by. The waste products are relatively innocuous. It certainly avoids the low pH. But certainly we need to do more research to really prove that this is not impactful to the ocean environment. It's not energy or technology intensive, certainly relative to, say, molecular CO2 capture with geologic storage. And it really just simply modifies, really a modification of what's already being done in the coal power industry with desulfurization. And we think, we and others think, there's actually been another estimate done on this technology, think that maybe you could mitigate 10 to 20% of U.S. emissions at less than $30 a ton CO2. Would this make sense in California? Well, I got a hold of a geologic map of California that identified all the known limestone mines and reserves. And I've simply outlined here in ovals some of these major deposits on top of a map here of the power plants here in California. And as I recall, I don't know whether you can see this very well with the lighting, but the red dots here are your conventional gas or in some cases coal-fired power plants. So there is a concentration of power plants coastally located, and in some cases limestone is very nearby. I point out here that one of the largest plants, power plants here, gas-fired plant, is in Moss Landing, California, which is also very close to a major dolomite limestone mining region, just about 10 miles away. So in some cases here, it appears that the transportation costs and availability would make, could be favorable for employing this kind of technology. What else needs to be done to further this research? Well, obviously, we're going to be limited in the sites where we could do this, although it's possible we could overcome this by piping CO2 to the ocean if that were practical and feasible and acceptable. Alternatively, there might be some inland water sources that we can use, and I'll talk a little bit about that shortly. Marine impacts. We think that there potentially is a net beneficial impact of this. It's been shown that adding bicarbonate to marine systems actually stimulates calcification, and some saltwater aquarium enthusiasts actually use a miniature version of this reactor to generate alkalinity to stimulate or to preserve calcification for their pet animals. But nevertheless, this would need to be, further research would need to be done to prove that this is not impactful to the marine environment. Certainly there would be impacts associated with the mining and transportation of carbonate that would need to be taken into account. And certainly we would need a better assessment, both regionally here in the state and elsewhere, as to when and where this kind of technology might make sense. There is a somewhat related opportunity for CO2 mitigation in cement manufacturing. Now, as you probably know, cement manufacture is a very carbon-intensive process. Something a little over 10 million metric tons of CO2 are emitted per year in this state, and the cumulative emissions between now and 2020 are going to be like something like 260 million metric tons. The CAP report in 2005 identified cement manufacture as one of the opportunities for CO2 reductions, and they argued that with the using certain blends of cement with fly ash or limestone, or using alternative fuels in the making of cement, could lower the CO2 emissions from this process by something like 47 million metric tons by 2020 at a relatively modest cost. But there's been some resistance to these various possible mitigation routes, and certainly other ideas need to be thought about and looked at. And one idea I had was, in addition to CO2 being emitted in the cement manufacturing process, typically there's also a very alkaline waste stream that's generated called cement kiln dust, and it's principally made of oxides and hydroxides of calcium, sodium, magnesium, potassium, etc. It's a very alkaline waste. When it's typically moved around as a slurry, and the slurry is very alkaline, pH in excess of 12 or so. And it seemed to me that given that you're generating a very acidic or a relatively acidic stream here with the CO2, and you've got a very alkaline stream here that's already potentially in a slurry form or an aqueous form, that this could react be readily reacted with CO2 to form calcium carbonate or other metal carbonates that could be precipitated out, and thus you would have a carbon capture and storage scheme where you could store it as carbonates of the various metals that would be in this mixture. Or in theory, you could perhaps selectively precipitate calcium carbonate, separate that from the other products, and recycle that as starting material for your cement. So some of the features and issues here, well, it sort of asks the question, could we kill two birds with one stone? Could we not only mitigate CO2, but also mitigate this very alkaline CKD problem, which is actually an environmental problem of its own? Could we simply, by combining them, neutralize both and also capture CO2? Could we recycle the calcium carbonate that might be generated from this? And also, could the other carbonates that form be of commercial use, such as fertilizer or what have you? This should be pretty low cost, perhaps less than $1 a ton, because we have all the starting compounds here. We're simply using waste streams, and so the real cost here would be the energy in moving this stuff around and contacting it. And obviously we need to do more work in evaluating the strategy, and I do have a proposal in with the Portland Cement Association to take a further look at this. Another opportunity for sequestration is in oil production. As you may be aware, there's actually more water brought to the surface than oil under normal oil lifting. On average, something like 10 barrels of water are brought to the surface for every barrel of oil. Given that California produces about 550 million barrels of oil a year, if this ratio is correct, then we've got a few gallons of water that are being brought to the surface, and for the most part are being put back into the ground. This water typically is not potable, and it also may be contaminated with things that you would not want to put into surface waters. Plus, it's also effective to re-inject this water to maintain reservoir pressure to allow oil to be further brought to the surface. So for a variety of reasons, most of this water is re-injected into the ground. Another thing is looking at some of the chemistry of this in some Texas-produced waters that I looked at. This data is from USGS. This water tends to be alkaline and will tend to absorb CO2. If you wanted to, you can enhance that absorption again by adding alkalinity or adding limestone to it, but that may be unnecessary or may not be cost effective to do that. But in any case, if you're bringing this water to the surface and simply pumping it back in the ground, one could, in theory, very easily equilibrate at least some of that water with waste CO2, charge that water with CO2, put that back in the ground, and in fact have a CO2 capture and storage capability at relative what should be very low cost. There could be some other co-benefits of doing this. Scaling of the water handling facilities in oil production is a big problem. And looking at their scheme, I can see why that's the case, because in many cases they take CO2 out of the water, or they try to aerate the water or remove the CO2 that's in there. That'll elevate the pH and obviously precipitate carbonates and will enhance scale. If you add CO2 to that, you will obviously depress the pH, and you should reduce scaling and potentially microbial fouling. Obviously, more work would need to be done to prove that, but this is a potential benefit. There also might be some enhanced oil recovery potential here, adding CO2 underground. CO2 is miscible with oil, and in some cases, molecular CO2 is pumped underground to enhance oil recovery. Maybe that could also work here. And there might be some benefit in oil-water separation, which is a big issue in oil recovery. So this is just a little scheme of what is typically done. You bring oil and water to the surface. There's an initial separation of the oil, of the gases, the oil in the water by various means. This goes into some secondary separation where they do further oil-water separation, again extracting the oil. Ultimately, the water is then pumped back down in the ground. Could we modify this scheme to either recapture the CO2 that's lost in this initial aeration or add other sources of waste CO2 to it, with or without additional limestone? Maybe the water's alkaline enough to itself to affect the CO2 capture and storage. So we charge the water with CO2 or its products and simply put that back down on the ground as a way of having low-cost local CO2 capture and storage. Okay, this is a little different scheme. Again, aqueous chemistry. It's fairly well known and appreciated, especially in the oil and gas industry, that iron does corrode in the presence of CO2 and water, forming iron bicarbonate and generating hydrogen. You can take this a step further. You could precipitate this iron bicarbonate as iron carbonate by degassing excess CO2. So the net process, in theory, would be a way of capturing CO2 by reacting it with iron and water, precipitating the captured CO2 as a solid, generating hydrogen, and also generating energy. If you set this up as a fuel cell, you could also generate electricity, in theory. So at the anode, you're basically oxidizing the iron, and at the cathode, you are reducing the hydrogen. And current density and voltage have been measured in these situations, especially in the context of corrosion. They haven't been measured actually in the context of a fuel cell like this. I have no idea what the Optimum fuel cell would look like. I haven't built one of these, but one can imagine that there's an anode and a cathode and an electrolyte composed of water charged with CO2. Say at a larger scale, what would this look like? You'd have a fuel cell battery array here that you would feed scrap iron. You would feed it waste CO2, and you would feed it water. And the output would be, in theory, you have some sort of hydrogen cleanup here, hydrogen generating electricity and generating a carbonate solid. Again, I haven't built one of these cells. This is all theory, but it's another example how perhaps we could employ chemistry to not only capture CO2, but maybe generate hydrogen and electricity. This is sort of the stoichiometric ratios of the inputs and the outputs. What would this cost? Well, it's very much dependent on what the cost of your reactants are and what the value of your products are. This is a very rosy analysis where I assume that scrap iron could be had for $35 a ton. I assume that hydrogen here can be sold at $2.80 a kilogram, which is at least twice what it currently is, the hydrogen cost commercially. But again, depending on the values of these reactants and products, there would be either potentially a profit or a cost, depending again on what the values of these were. And as an example, here's just a function of the capture and sequestration cost as a function of the value of the hydrogen that you're producing. And by my estimate, you can get a zero cost here if you can sell your hydrogen at $2.80 a kilogram. This is actually under what I think the current green hydrogen schemes would be, say from biomass or other non-fossil sources, but obviously is a lot more expensive than commercial hydrogen that's generated from methane. Could we capture CO2 from air? If we could do that, we could solve a lot of problems. If we can do this cost effectively. This would mean that we wouldn't have to sit at the end of a tailpipe and capture CO2, that we wouldn't have to chase around cars or reduce emissions from cars. We could simply have locations where we have some sort of super CO2 sponge that would absorb CO2 out of the atmosphere and therefore solve all of our problems, or at least some of them. Is there a way to do this that would be cost effective? Well, certainly nature already does this. As I pointed out, photosynthesis is a way of absorbing CO2 from air. There's been some discussion about doing this in a more intensive way. Could we have islands of genetically engineered plants that would very rapidly or more abundantly take CO2 out of the air, more efficiently use photic energy to do that, and make products that would be more stable? That's certainly one idea. The other way to do it is chemically. Certainly it is well known that CO2 will react with hydroxides. Here in this case is calcium hydroxide, but you can have sodium hydroxide, potassium hydroxide, whatever. And in certain industrial and experimental and chemical settings, these hydroxides are used routinely to capture CO2. But to do this on a large scale would be extremely expensive. Making these chemicals are costly and they're very carbon and energy intensive. Is there a cheaper way that one could generate chemicals that could act as absorbents for CO2? Well, here's another idea, and I'm not going to tell you the whole story here because I'm still working on it, and I don't want to divulge the whole detail. But this idea is really an electrochemical idea, and it involves electrolysis of water, which will generate oxygen and hydrogen, usually, although not always. I think I have an idea for modifying the chemistry in here so that one could generate compounds that would absorb CO2 in solution to the point where there would be a real gradient in CO2 concentration, and CO2 would diffuse into this water. And so one can envision, I don't know, a lake, a reservoir, an ocean, whatever, where you were doing this process slightly or even significantly modifying the chemistry so that you have, in effect, an atmospheric CO2 sponge that would suck CO2 in solution and keep it there for as long as you wanted. This is one idea. There are other ideas about air CO2 capture. It's something that it's a very noble endeavor. Whether we'll ever be able to do it cost effectively remains to be seen, but it's something that's worth thinking about. Well, the bottom line here, as you've gathered, is that I'm a fan of chemically reacting CO2 out of waste streams. It seems to me that we ought to exploit this reactivity as we did in the case of SO2 mitigation. CO2 is a reactive compound. It will react. Are there reactions that would be cost effective to do, that would form stable or benign products, that would allow us to do at least some of the CO2 mitigation that is going to be required in the coming years? And so on that note, I'll just conclude and say that I think CO2 sequestration needs to be part of California's thinking and strategy for meeting its CO2 emissions. Perhaps the reason it hasn't figured so prominently is the concern about, I would say, the most commonly discussed form of sequestration, which is molecular CO2 capture and geologic storage. I think there may be cheaper ways to go, going the chemical route, and therefore, because there are some alternatives, I think it needs to be included here in the thinking about how California is going to meet its emissions goals. And I think in the long term, we're going to need carbon sequestration because we're going to continue to use fossil fuels, not just here but globally, China, elsewhere. They are not going to forgo the use of fossil fuels, and increasing efficiency is a good idea, but that simply forestalls CO2 emissions. Whether we emit all of the CO2 over 200 years or 400 years, ultimately the CO2 will get into the atmosphere if we do use fossil fuels. Therefore, we need to think about ways of reducing the CO2 footprint of that use. As I tried to point out, there are some ideas here for cost-effective and safe chemical CO2 sequestration. We need to do further research on these ideas, and I and others are actively seeking partners and funding to continue this work. And finally, I'd just like to thank some of my colleagues, Ken Caldera at Lawrence Livermore National Lab, now at the Carnegie Institute at Stanford, Kevin Knaus at Lawrence Livermore, Bill Langer, carbonate geologist with USGS, and Julio Friedman, who heads the carbon management program at Lawrence Livermore National Lab. So if you need further information, you can ask me now or contact me at my email address. So thank you very much for your attention.
Well, thank you, Dr. Rao. We'll have some questions and answers now, and I'll remind the audience that since this is being webcast, we have to use the microphone. We did receive 4 via email, and I did notice that our handout was incomplete. It only has half the slides, so if you want the full slide presentation, it's on our webpage. And so the first question comes from Scott Anders, Director of Energy Policy Initiative Center at the University of San Diego School of Law. And his question is, carbon capture and sequestration is often used in the context of coal-fired power plants. California has very little, if any, coal production. Does the speaker recommend using CCS, carbon capture and sequestration, I'm guessing he means by that, with natural gas-fired production, or applying it in some way to industrial processes and transportation applications?
Well, I think CO2 capture and storage is applicable to any waste stream if it's concentrated enough and if your process is effective in reducing CO2. I know there's been a lot of interest in mitigating, capturing and storing CO2 from coal plants, but there's no reason that it needs to be focused on coal combustion. In my view, at least some of the chemical approaches that I've talked about today, I think it would make more sense to do these chemical capture storage processes on gas-fired power plants, because you're starting with a much cleaner flue gas. You don't have to worry about sulfur emissions. You may have to worry somewhat about nitrogen oxide emissions, but it's a much cleaner CO2 stream. If you're going to put this in the ocean, that's a real consideration. I think I would want to think twice if I was going to apply this accelerated weathering of limestone to a coal-fired plant, because of all of the potential contaminants that would be put into the ocean by that process. So in my view, carbon capture should be broadly thought about for any waste stream, and it may ultimately turn out to be easier to do this on gas-fired plants than coal plants, but I think we need to think about all options in applying this.
Thank you. Scott also had a second question, follow-up. Could you explain the process to purify CO2 to be mitigated, and why is this necessary for CCS?
Well, that's a good question. My understanding is that the reason that you want to purify the CO2, one of the reasons at least, is to avoid contaminants in transporting this gas stream by pipe. There are apparently significant corrosion issues if there are significant amounts of water or sulfur or other compounds in the gas. So if your scheme is to capture CO2 and then transport that by pipeline to where you're going to put this underground, it would best be done with as pure a CO2 stream as you can do. So I think one of the drivers for purification here is to reduce the corrosion aspects, but also from a transport aspect, the purer the CO2 stream, the more efficient the transport is going to be. So you're not carrying along with it other contaminants. You can more efficiently transport CO2 per unit of energy put in for pumping, for example. So that may be another motivation for purifying the CO2. But it's also a costly thing to do. It costs you money to purify CO2 from a dilute and contaminated initial flue gas stream. So that it's an expensive proposition.
Thank you, Dr. Ra, for an excellent presentation. A point of clarification and then a question. First, I think in general we will agree with you that capture and sequestration is going to play a significant role in what we do here in California. And an example of that is the fact that the actual legislation, the AB 32 bill, does call out specifically CCS as perhaps one of the strategies that we are mandated to consider. So just that point of clarification. But the real question is, can you give us perhaps a real brief synopsis in terms of the status of this particular approach worldwide? Because in your optimal scenario, at less than $3 a ton, that is very competitive if you consider, for example, that in the European trading system right now, carbon is trading at about maybe 2 or 3 times that cost. So has that emerged as a real solution elsewhere in the world?
Not that I know of, and I'm not sure why that is. I don't know whether I know that some people worldwide are aware of this idea. There may be some reluctance to pursue it because there hasn't been a lot of R&D done on this technology. But I think sooner or later, in certain settings where it makes sense to do this, it will be pursued. It may not be the U.S., it may be elsewhere. I might also say that there are places in Asia and elsewhere that are using seawater scrubbing for SO2 mitigation. So there's already technologies in place there where they're pumping and using seawater for emissions reduction. Why not modify that slightly, and you could also do CO2 mitigation also. So to answer your question, I don't know why this hasn't penetrated, become one of the mechanisms for CO2 mitigation, but I think sooner or later it will be seriously considered and at least tried.
Dr. Rao, here, a follow-up question from the email. This is from Steve Hill at Sierra Research, and he says, you analogize CO2 scrubbing with existing SO2 scrubbers. Those scrubbers are on combustion sources now. What is the measured CO2 abatement efficiency on these existing scrubbers?
You mean CO2 capture, or does he mean SO2 capture?
Measured CO2 abatement efficiency. If he types real fast, he can clarify this. No.
Are there CO2 mitigation technologies employed right now? Not that I know of. There's certainly SO2 mitigation technologies that are employed. I might say, possibly related, if you do wet limestone scrubbing in the context of SO2 abatement, you actually generate more CO2. I don't know whether you remember the equation I showed you, but it actually decarbonates the limestone and generates CO2 in that process. One of the things we thought about, is there a way of combining SO2 mitigation and CO2 mitigation in one reactor? It may be possible. Maybe we could have one large reactor that does it all, or maybe a sequence of reactors where you initially take out the sulfur and then the next one you take out the CO2. We thought about that. Obviously, we need to do research to see if any of that would make sense.
This is Jared Demas from the Energy Commission. The graph that you showed earlier, one of the ones we didn't get a copy of, you said was about 1 million years for nature basically to scrub out the carbon dioxide, and you called this an accelerated weathering of limestone. You didn't really address the time scale. How long does it take? You can accelerate it from 1 million years to 500,000 years, but you haven't really done anything. So I presume this is something that happens rapidly enough that it really could be considered.
Well, certainly with the sources that you're mitigating, it will be rapid. Can we do all carbon emissions this way? I would say no, it's not reasonable that this alone is going to speed up be the mitigation method for rapidly reducing all CO2. I'll see. You want me to bring up that that particular slide? I'll see if I can. Well, yeah, this is the one, right? Carbonate, just see what happens initially is that there is an uptake by the ocean, which is obviously going on now. There also is a little bit of continental carbonate weathering. These curves are actually little curves that look, well, for example, mixing and uptake by the ocean, this is actually kind of like a curve that looks like this. So initially, what you've got is equilibration with the atmosphere and the mixed layer of the ocean. Ultimately, that gets mixed down into the deeper ocean. While this is going on, there's actually carbonate dissolution going on, but its contribution is much smaller. So there's a little peak here of carbonate dissolution, and then ultimately you've got silicate weathering going on. So all we're saying is where it makes sense to speed up this process by adding it to seawater and exposing it to limestone, you can do the mitigation of whatever source you're mitigating essentially instantaneously. You've compressed this that would normally take 10,000 years into an instantaneous conversion of your CO2 to bicarbonate that otherwise is going to take a long time to do if you simply release this to the atmosphere and let nature take its course. Now, to do all of this emissions by this technique, by accelerating weathering, is simply impractical. But there are settings and locations where you can speed up this process, and that's all we're arguing, is that one should think about doing this in places where this makes sense to do.
So you're saying in a reactor it's instantaneous?
Yeah.
Like a sulfur scrubber?
Yeah.
Okay. And I guess this is really just a concept right now?
It's a concept. We've published papers. We've done some bench scale work on this to sort of confirm the rates at which this occurs. The next thing that needs to happen is a pilot scale or larger scale demonstration of this technology. And also what needs to be demonstrated are the environmental impacts. That we're assuming here that the impacts to the ocean or wherever the solution ends up, we're assuming those impacts are acceptable, and we need to prove that that's the case.
Might as well just do the last one from the email. This is from Michael Endicott with Tres Amigos Verdes. How will stimulating calcification in the ocean affect bloom potential? Have any studies been done that examine this?
No studies that I know of. Certainly we would need to do, again, research on the environmental impacts of adding bicarbonate to the ocean. I would point out that if we don't do anything, and including not mitigating CO2, there will be significant effects to calcification in the ocean and biogeochemistry in the ocean, including phytoplankton. So we may get to a point where we need to actually mitigate the impacts of CO2 on those kinds of organisms. If that happens, then this is a way either to avoid that or to mitigate that by adding, in effect, components like bicarbonate that appear to stimulate calcification. But obviously that scheme would need to be researched and studied, and we need to prove that that in fact would happen and would be a benefit and would help to offset the loss of calcification that's occurring otherwise.
On your slide for the proprietary water body sponge approach towards uptake of CO2, there's likely to be some mass transfer limitations that will be involved, and the efficiency is going to be a function of surface area. Any guess as to the total ballpark amount of surface area that you're going to need to achieve any desirable amount of CO2 sequestration?
Well, certainly there will be inefficiencies there, but we've got a big ocean out there. We've got 70% of the Earth is a big water body, and just imagine that we have a few things floating out there that might slightly alter the chemistry of the surface ocean out somewhere in the middle there. We could have a very large surface area that could act as a sponge. But certainly that would need to be looked at. What size are we talking about? How much could we do? How fast could we do it? What would it cost? And also there's an energy cost there. It is electrolysis. The steam I showed you was solar powered. Would this be effective to use conventional electricity? Would you still get a net carbon gain if you used natural gas-fired electricity in that setting? So there's all sorts of questions here of how effective it would be and what the consequences would be and the cost. So it's really more of an idea than something I can give you a lot of detail on here.
My name is Steve Doyle with Clean Energy Systems. You had an acronym on one of your slides referring to industrial cooperation between Lawrence Livermore and other companies, the companies in the industry, BP and CES.
Yeah.
We're the CES. We've been working with Lawrence Livermore off and on over the last 10 years on separation and capture of CO2 and oxy-combustion of fossil fuel, and have demonstrated with a power plant operating in Bakersfield for the last 2 years, funded by the California Energy Commission, that you can burn fossil fuel with oxygen and produce zero emissions. That's a fact. We have that technology now proposed for Westcarb. We have submitted a letter of commitment to the California Energy Commission for that. And we couldn't agree with you more that fossils are not going to be foregone, because they are the basic fuel capacity for our energy requirements for at least the next century, if not longer. So we need to learn how to work cleanly with fossils. In listening to your presentation, a lot of the things that you covered I have seen covered previously over the last 2 or 3 years by people at other national laboratories. And I'm wondering if you're familiar with the work, for example, that's been done by Sally Benson at Lawrence Berkeley, where she's done a lot of study of available resources for sequestration in the state of California and concluded preliminarily that there are 300 years of storage capacity for sequestration of carbon dioxide available in the state of California alone. Those kinds of capacities would encourage one to look seriously at ways of capturing, separating and capturing the CO2 inexpensively. The other national laboratory that's done a lot of work on the solidification of the CO2 that you've talked about, I've listened to presentations they have made, and one of the things that they said was that you need a power plant in the order of 1 gigawatt of emitted power to justify the costs associated with bringing in, mining and bringing in the limestone and then processing the CO2 against the limestone, that this can't be done at 100 megawatts or 200 megawatts on a cost-effective, competitive basis. You've got to have big plants supported by rail systems, and you've got to be able to bring in the limestone and take out the limestone by rail. So there's an inherent cost associated with that. And then on many of the things that you identified as theoretical, they talked about those things being resolvable. They're all resolvable with time and money, as you point out. But they're 3 to 5 years individually, and collectively maybe 15 or 20 years to come to solidification as a means of sequestering CO2. So I just wanted to bring these realities before the audience, because a lot of what you talked about is theoretical, and it's valuable to have these kinds of things studied. But I just wanted to mention that Clean Energy Systems has an operating power plant burning fossil fuel today with 0 emissions. So that is not a technology that's far away. That's a technology that's in hand. And you're exactly right. The CAT report didn't even mention it.
Well, this is Mike Fitzgibbon on behalf of the Research Division and the Air Resources Board. We'd like to thank Dr. Greg Rao again, and thank you for coming today.